Okay, so now we've talked about the moments of inertia, we've talked about the radius of gyration, and we've talked about the product of inertia. Well, kind of implied in all that is the moment of the area moment of inertia and the area radius of gyration. Now we're going to talk about the moment of inertia of a mass. Okay, so it turns out that angular acceleration about some axis, right, of the small mass of this small mass here, given a couple, is proportional to r squared dm. In other words, the moment of inertia of a mass is the equivalent. So you have your F equals ma equation of just Newton's law. You force equals mass times acceleration. Well, it turns out that your mass, the equivalent for angular acceleration stuff, is going to be your mass moment of inertia. So this is kind of getting into the world of what you're going to be doing in dynamics. Okay. So r squared delta m is the moment of inertia of mass, right, with respect to the axis. And so when you have a body, right, so your really funky shaped potato here, it has some mass. Its resistance to rotation about the axis is its product of inertia. So it's going to have, so I said its product of inertia. I'm sorry, its mass moment of inertia. So I is the integral of each individual portion, right? R1 squared delta m plus R2 squared delta m plus R3 squared delta m, and so on. Which, when you do that enough, you end up integrating it up, and its integral of r squared dm is the mass moment of inertia. So that is the mass moment of inertia. So it's obviously very similar to the area moment of inertia, but it's not always the same. The radius of gyration for a concentrated mass is, again, same deal. The k ends up being I over m, right? And so let's talk about the moment of inertia with respect to the y-axis. So we talked generally speaking here, right, that it's integral of r squared dm. So, but the moments of inertia we've talked about, they only make sense with respect to n-axis. So the moment of inertia with respect to this y-axis is going to be what? It's r squared dm, right? We talked about that. Iy is integral r squared dm. What is r squared? R squared is x squared plus z squared. Remember, we're talking about from this y-axis. It's going to be different for different axes, right? So Iy is integral r squared dm, which is z squared plus x squared. Now, if you start considering the other axes, it's going to be the same deal. With respect to the x-axis, now what is your r? It's going to be y squared plus z squared, and z is y squared plus x squared plus y squared. So when you talk about the units, you're going to looking at r squared dm. So you're looking at a mass and a distance squared, so kilogram meters times meter squared. In our U.S. customary units or in English units, it gets a little more complicated. It's still mass times distance squared, right? But when you actually look at what these masses are, it works out to be pound foot per second, not per, pound foot times second squared. Okay, so let's consider the parallel axis theorem for the mass moment of inertia, right? So you have a rectangular axis right here, and then we want to figure out what is it with respect to some other axis. Okay, so how do we do this? Well, it turns out your Ix is integral y squared plus z squared dm, right? So that hasn't changed. But since we're talking about parallel axis theorem, we're going to say, hey, this y is really some distance to the centroid of that object plus some additional distance, right? And same with the z, some distance to the centroid plus some additional distance. So when you go through, you multiply it all out, and you hopefully will recognize this as looking pretty similar. What is this term right here? Well, first off, let's look at this term. This term, if it's through the centroid, that goes away, right? Because this is the first moment, and the first moment through the centroid is 0. This is the first moment with respect to z, so it goes through 0. And then excuse me. So if that goes away, and then hopefully you recognize this as the I bar term, and then you have your additional term. So you have Ix is Ix bar plus mass times the distance squared, Iy and Iz. So it works out to be the same. So that, to make it kind of just general is I, this is, so hopefully this looks familiar, right? Your moment of inertia about any axis is its centroidal moment of inertia plus the mass times the distance squared to that axis. So that's how this works out. So again, parallel axis theorem, it only makes sense if you're doing it through the centroidal axes. If not, these terms don't go away, and then all of a sudden the equation is not this simple. I mean, if you wanted to make your life really, really hard, you could do it from any two axes, but then you'd have to figure out these terms as well. This is what we're calling the parallel axis theorem, and that requires that you pass through the centroid of the object. Okay, so now let's talk about some examples kind of simplifying the mass moment of inertia where it's related to the area moment of inertia. Okay, so say you have this plate. So we have this this thin plate, okay, of uniform thickness and homogeneous material. So in other words, its mass at any point in time, if you take the same little area, it has the same mass anywhere in here. Okay, the mass moment of inertia with respect to this axis is what? Well, it's integral of r squared dm, right? Which is r squared times dm. Okay, what do we know about dm? Dm is the differential mass of this little spot. Well, that is, what is the differential mass? Well, it's its area times its thickness times its density. But we already said that it has uniform thickness, so a constant thickness and a constant density. So the rho t can pull out of the area and then end up with rho t r squared dA, which you should look at and say, hey, I recognize that. So what this is saying is that the mass moment of inertia of a thin plate is equal to the density times the thickness times the area moment of inertia of that same plate. Okay, now let's consider, so we did this axis in this direction, now let's look at this axis in this direction. You're going to find that it's the same deal. But then when you consider, hey, what about the moment of inertia with respect to an axis that is perpendicular to this thin plate? Hopefully intuition says that might be a little bit different, and it actually is, as you thought about it. It's going to be different. And how is it going to be different? Well, now you're going to be using the polar moment of inertia, right? So ICC is going to be the mass times the density times the thickness. But now it's times the polar moment of inertia, and that makes sense, right? Because this is rotating. It's asking how much does it want to resist rotation in this, around this axis, and so it's the polar moment of inertia that's going to be affecting that, which works out to be rho t times the area moment of inertia in x and y, right? That's what we talked about earlier on in these slides. We talked about the polar moment of inertia is just the sum of the x and the y moments of inertia, and so it's the same deal. Okay, so again, some moments of inertia of the thin plate. We just talked about this, right? So for the principal centroidal axis on a rectangular plate, we just talked about this. You pull out the rho t times I area, right? Well, we know what a thin plate is through the centroid. We talked about right here, right? So we're talking IAA right now, right? So what is the centroidal axis? It's 1/3 BH cubed. Well, if it's respect to this axis, the base is in this direction, so it's oh, I made the mistake. I made the mistake that everyone is going to make in this class. I just said 1/3 BH cubed. What is 1/3 BH cubed? 1/3 BH cubed is with respect to this axis. Don't make the mistake I just made. Okay? With respect to this axis, it's going to be 1/3. With respect to the centroid, it is 1/12. Okay, so 1/12 BH cubed. So 1/12 A cubed B. So the mass moment of inertia of this thin plate is rho times t times the area moment of inertia, which is rho times t times 1/12 BH cubed. Okay, but we're going to go past that. This is absolutely correct. This is accurate. This is all good. But it's not overly helpful, right? Because so someone gives you, say, a washer or a little flat piece of metal. Okay, you don't necessarily know the thickness, and you don't necessarily know the density. What do you know? You can put it on a scale. How much does this thing weigh, right? You know the mass of it. Okay, so what does that mean? The mass is area times the thickness times the density, right? Or m is AB. So the area of a rectangular plate, right, is this distance times this distance times for the mass is times the thickness times its density. That gives you its weight. Okay, sorry, that gives you its mass. So plugging that into the equation, right, this rho t is going to cancel out, and you're going to lose some of this stuff, and you get that the IAA is 1/12 MA squared. So although this is totally true, it's not overly helpful. This, however, is helpful because you can put it on a scale. You can quickly measure what the mass is of something, right? And then you can get, so you know that the mass moment of inertia with respect to this axis right here is 1/12 times mass times a squared. And it's also for the b, it works out to be the same thing for the with respect to this axis here. So it's 1/12 mb squared. And so we just talked about in the previous slide, this with respect to this axis here through the axis, the c prime axis, it's just the sum of the two. So it's going to end up being 1/12 m quantity a squared plus b squared. So that's for a rectangular plate. For a centroidal axis on a circular plate, it's using similar logic, right? Do the same basic idea. We're going to find that IA is IB through symmetry, right? So it's rho t times 1/4 pi r to the fourth. Okay, but again, remember the mass is the area, pi r squared, times the thickness times its density. So that comes and it cancels out on this end, and you end up with the mass moment of inertia of this axis, the x or y axis basically, right, is 1/4 mr squared. So you notice this r to the fourth goes away because of this r to the fourth in here. So it's 1/4 mr squared. And again, the polar moment of inertia is going to be, you just add the two of them together, and since they're the same, you can just multiply by 2, so it's 1/2 mr squared. Okay, so now let's talk about the moments of inertia of a 3D body by direct integration. So there's certain times when you can actually figure it out by direct integration. So moment of inertia of a homogeneous body is obtained by triple integrations of the form integral of rho r squared dv. So a homogeneous being that rho is constant, right? So integral of r squared dv. But dv is dx, dy, dz, right? No one wants to do triple integrations. It makes life a little bit difficult, okay? But we have some special cases. When a body with two planes of symmetry, so for example, look at this. This is symmetric with respect to the z and y axis, right? It's rotated around this x-axis to form a thing. The moment of inertia can be obtained from a single integration, right? You can go, instead of a triple integration, you can drop that down to a single integration if you choose a dv appropriately, right? So how do we pick that? Well, all of a sudden, look at this. If we pick this little disk, you have this disk. As this moves along, at any point in time, you can have this dm. So what is this dm? It's the differential mass, right? So the differential mass is going to be what? It's going to be the area of the differential disk times its thickness times its density. So dm is rho times the area times its thickness. The thickness of this thing is just dx. It's just a little thin slab. And so you can go through and integrate that out to figure out the moment of inertia of this three-dimensional body. Again, for a pretty specialized case when there has two planes of symmetry. And so it's also important to notice that the moment of inertia with respect to a given axis for a composite body, right, can be obtained by adding all the individual things. Just like we've done in 2D, now we're doing the same thing in 3D, right? You can add the mass moment of inertia of each one with it, as long as you hold the axis similar for all of them. So we have this table in the book, right? You have this table with all these kind of known 3D parts, right? You have a rod, a slender rod is what they call this. So 1/12 ml squared. You have a not so slender rod. So if you'll notice, what's the difference between this and this? So it's 1/12 ml squared, but now you also have the mass of the thing itself. So you have the 3a squared. You have a washer or a disc, right? It has mass moment of inertia. So you can look up these portions and you can build together. You can calculate the mass moment of inertia of a given, body based on its individual components. So let's do just that. Yay, the excitement. Let's do an example problem of doing just that. This is example 9.12 in the book.